This is the video on charge and current. So in these videos, there will be two codes. One will be a written code that'll pop up on the screen. The other code will be a verbal code said by myself at some point in the video. You'll need all the codes in order to move on with that homework assignment. When you're looking at these slides or watching this video, what's important is going to be highlighted in green. That'll be like what you should write down. The rest is just really good information for you to have. So this is the weekly review written code. I would recommend you write this down somewhere. All right. So when transferring charge, why are electrons transferred and not protons? So let's just take a look at that. So protons and neutrons are held together in the nucleus by the strong force, while electrons are bound to the atom by the much weaker electromagnetic force. This means that it is a lot easier for electrons to be stripped away from the atom. That's the whole idea behind electrostatics. So for all of these problems, anything you're talking about electricity, you need to answer, well, what do like charges do and what do opposite charges do? So you can see here, there's a little diagram. Well, like charges repel, opposite charges attract. That's just the key behind electrostatics. And what will the electrons do? Because remember, the electrons are going to be the one that the part of the atom that's going to be moving around. So an electrical conductor allows the flow of electricity through them. Electrical insulators do not allow the flow of electricity. Now, because this electrical effect could flow through things and behave like a fluid, people began to think of it as an invisible fluid that would flow through one body and into another, like water flowing through a pipe. You can see here we've got electrical conductors. That's like, metal. That's going to allow the flow of electricity. And electrical insulators such as glass, plastic, rubber, they do not. Or it's very hard for the electricity to flow through them. Now, it was Benjamin Franklin believed that there was just one kind of like fluid, and it became electrified. This meant that you either had too much or too little of that fluid in that body, and thus, in trying to equalize the amount of fluid, objects would either attract or repel from each other. So Ben Franklin was the person that came up with the terms positive and negative for charges. Now, these are just words. He could have called them anything: up, down, left, right, back, forth. And believe it or not, like if you zoom in to the atom, there's not little positive or negative signs written on the protons, neutrons, and electrons, right? It doesn't really just tell you. He just came up with those terms. So this is like the important conclusion here. That brings us to the law of conservation of electrical charge. Charge can neither be created nor destroyed. Charge can only be transferred from place to place. And that's the whole idea behind electrostatics, charge being transferred. And the fundamental rule at the base of all this: like charges repel, opposite charges attract. So think about like a magnet, and it is the electromagnetic like force that's doing this. You get two positives, two negatives, they're going to push away from each other. You get a positive and a negative, they're going to attract to each other. So because electrons are easier to remove from the atom than protons, when you rub one material against the other, some of the electrons get transferred from one object to another. Protons do not get transferred, and that's because they're held in place in the nucleus by the strong force. Electrons are held in place by the much weaker electromagnetic force. So if an object gains electrons, it becomes negatively charged. If an object loses electrons, it becomes positively charged. So all that's been done is for charge to have been transferred, right? Like you do not gain or lose charge. The total amount of charge remains fixed. Like in the universe, we're just transferring charge. So polarization is the process of separating opposite charges within an object. So the polarization process always involves the use of a charged object to induce electron movement, electron arrangement. Electrons do not get transferred during polarization. So what this means is that if I have this like metal sphere and I place a positively charged rod next to it, well, those electrons are going to attract to the positive charge and they're going to move to one side because metal is like a conductor, and it's going to be those electrons are able to flow freely towards that charge. That's polarization. I'm separating it between positive and negative. Now, charging by friction is the process of transferring electrons by rubbing the total amount of, or by rubbing objects together. The total amount of charge does not change. What changes is what object has more electrons. So you can see here these nice graphics showing you them being charged. Like the electrons are being transferred by rubbing them together. Now, charging by contact is the process of giving one object a net electric charge by placing it in contact with another object that is already charged. So if we look at this, like just think about this way, right? If I've got a negatively charged object, right, like a negatively charged rod, those electrons, those excess electrons are trying to get away from each other because like charges repel. And if you touch that rod, that charged rod, to something like the metal sphere where they're able to spread out, yeah, they're going to take that opportunity and go into that object and charging that object. That's how you charge by contact. Now, charging by induction is a process of bringing a charged object near but not touching a neutral object. The presence of a charged object near a neutral conductor will force or induce electrons within the conductor to move. You have to polarize it first, right? Then the object is grounded to charge that object. So you can do this two ways. So you can see your polarization over here, right? So either positive or negative is just going to force those electrons to one side or the other. Now, when you ground it, what that's going to do is that's either going to give like electrons a chance to go into that object or out of that object, and that's going to charge it by induction, right? So that's the process of charging by induction. Now, the last thing, we did talk about grounding when charging by induction. Grounding is a process of transferring any excess charge of a charged object to another object of substantial size, like Earth, and it provides a pathway for electrons to or from Earth. So if an object is positively charged, grounding will provide a pathway for the electrons toward the object to become neutral. And if an object is negatively charged, grounding it will provide a pathway for the electrons away from the object to become neutral, right? And lightning is a form of grounding. So you can see here these diagrams. These are just groundings, basically getting rid of that excess charge, making it neutral by placing it next to a very, very large object like Earth, right, or ground. So what determines which object gains and loses electrons when charging by friction? So we did this lab, it's called Charge Determiner Lab, where we were rubbing 3 different types of rods with 3 different materials, and we had a negatively charged rod in the stirrups, and we were going to see if it attracted or repelled. Based on that, we could tell, well, what is the charge on that rod? And we could say, well, which way did those electrons go? The whole idea was behind this was to look at the triboelectric series. The triboelectric series is a list that ranks materials according to their affinity or love towards electrons. Charging by friction is also called triboelectric charging. So what it means is that different materials want electrons more or less than the others. So if we look at the list over here, the materials towards the bottom of the list have a larger affinity or love of electrons and have a tendency to go negative when being charged by friction. The material towards the top of the list have a smaller affinity love for the electrons and have a tendency to go positive. They have the tendency to give up those electrons to the other material. And if two objects are being rubbed together, the material lower on the list will gain electrons and become negative. This was the whole idea behind that lab that we just saw. Now, when is current able to flow? So now we've talked about charge. Let's talk about current flowing through like the things, like the wires in the hall or the walls. So let's take a look at some bricks, right? So if I've got 3 bricks 1 meter above and one brick like 2 meters above, the bricks on the left have more gravitational potential energy than the bricks on the right. Now, the 3 big bricks just don't fall upward because they've got more gravitational potential energy. Now, the bricks will always fall from a position of a higher gravitational to a position of a lower gravitational potential energy. So let's take a look at a siphon, right? So there are 2 requirements for a siphon to work. Discharge reservoir must be at a lower position than a source reservoir and must have the tube filled with water to start a siphon. Now, water towers work in a similar way to siphons. Water flows from high gravitational potential energy to low potential energy. So when you turn on your faucet, what's happening is you're providing a pathway from that higher potential water to flow down to the faucet. And that's how a siphon works. Electricity is very similar to gravitational flow. So 2 conditions must be met in order for the flow of electric current. Number 1, there must be a difference in electrical potential. And 2, there must be a conducting path. Electricity flow is similar to fluid flow. Voltage is the difference in electrical potential, the cause. Similar to water pressure, and current is the flow rate of electric charge, the effect. It's similar to the flow of water. So you can see here, like the siphon or like some sort of like water flow is very similar to electricity flow. So what should you do if a power line falls across your car? Now, obviously, what you should do is stay in the car if you can, right? Just in case, until emergency arrives. But if you have to leave because of smoke or fire, you want to avoid touch potential. And that's what happens if you just step out of this car. There's down power lines. You step out of the car, you touch the car and touch the ground. You're meeting those both requirements, high potential, low potential, and you are the connecting path and current will flow through you. You also want to avoid step potential. So if you take a step, well, that energy radiates out through the ground, and well, you could be connecting a higher lower potential just like by taking a step, and the electricity will flow through you. So here's the steps that you can take. If you can stay in the car, obviously stay in the car until emergency services arrive. If you must leave the car, jump as far from the car as possible with your feet together. So you can go from high to low potential as long as you don't connect them. That's fine. When you walk away, shuffle away. So you don't want to take big steps away because that'll avoid connecting a higher lower potential. You want to shuffle away. So how can someone increase their chances of surviving a lightning storm? So obviously, if you have a lightning storm, then what you should do is, seek shelter, right? But you want to avoid taller things like trees because lightning will strike the trees. But similar to a down power line, wherever a lightning strikes, it's going to radiate out. So if you're taking a step away, you could be connecting a high to a low voltage or high to low potential, and that electricity could flow through you. So if you're stuck in a storm, what you want to do is like put your feet together and like crouch down. That way you're not connecting like a high to a low potential if lightning strikes around you, right? But like I said, seek shelter or stay inside. That's the best bet. Interesting fact is males are 5 times more likely than females to be struck by lightning. About 85% of fatalities are men, and the reason is because most lightning deaths, around 90%, occur while fishing or in open sporting fields like golf. So, like if you see here, the how to survive a lightning strike little demo is he dropped his golf club because that's where the majority, like in open fields, like that's where like most lightning strikes happen, right? Let's see here. Here we go. Let's see here. Why are four-legged animals more vulnerable to lightning strikes than humans? So, cows, I mean, obviously they spend most of their time in a field, so they're at a disadvantage there. But cows spend most of their time. If you look at the picture to the right, what happens? Cows' feet are farther apart, so there's a larger difference in electrical potential. So, if it gets struck, they already have that step potential built in. Humans don't because our feet are closer together. So now let's talk about current. So we said, well, what is, we talked about like, well, what enables current to flow? What is current, right? So current is, well, we talked about current is the flow of electricity, but how we measure it, the unit for current is the ampere or amp. 1 amp represents a considerable amount of charge. It's a flow of so many electrons per second. It's basically 1 coulomb of charge per second. So how we measure it, just similar to the flow of water, like we measure like water going into the house, you measure electric current with an ammeter, right? We're measuring the amperage going through a certain current. And that brought us to a simulation. It's called Ben's mistake. So this one is like Benjamin Franklin was huge in the magnetic like studies, and he just chose. He said, "I'm choosing this as positive, this as negative. I'm gonna say things flow from positive to negative, right?" And what he did was he just guessed. He just guessed. Now we know now that it's the negative charge that flows. It's the electrons that flow from that. But the reason why we didn't connect or correct it, and we still view it conventional current as flowing from positive to negative, mathematically it works out, right? It doesn't. We don't really need to change anything because mathematically it works out. He just guessed because he couldn't see those electrons moving. So at this time, I'll go ahead and give you the verbal code. The verbal code is 712. I say that again. The verbal code is 712. So, how is the discovery of electric charge indirectly responsible for American independence? Well, like I said, Benjamin Franklin was huge. As like a rock star, and like because he could describe the electromagnetic, force, and you could predict it. And he was over in Europe during the time of the American Revolution, and he was very good friends with the King of France, and he was able to use his influence to basically convince France to uh, like help America out in the American Revolution. So sort of indirectly responsible, just a little bit of history, but Ben Franklin did do a lot with the electromagnetic force. So once again, this is where I leave you with just some final thoughts. There's too much unknown in the universe to take a break from learning. Get out there and question everything.